Okay, hi. I'm Lionel, and I'm going to talk about tree matchings with behavior trees. So the aim of this presentation is to explain how to organize subtrees into a complex and deep trees of data. It is related to Python, but you could use these techniques in any language that support reflexivity. So we are going to speak about behavior trees and to define it. And so after that, I will try to explain why we need tree matching and in a common use case for using tree matching. And during all the presentation, I put some code to explain how to do all this stuff. So what is a behavior tree? A behavior tree, in fact, as basically a diagram or schema that represents a process. That presents a process that describes different tasks. It's useful and very used in video games. For example, to describe the artificial intelligence of a boat, or the behavior of the boat. For example, here I could explain a boat in the game that cross a door. So I begin to describe with an arrow symbol a sequence of tasks to be executed. So I begin to say to my boat, begin to walk to the door. Behind this task could be used a pattern, a pathfinder algorithm to find where the door is, for example. After that, do a complex subtree, a complex subtree that is described, that begins by a question mark. A question mark is another abstraction provided by behavior tree, and the arrow symbol means sequences, but the question mark, in fact, is called selector. A selector in behavior tree is a list of tasks, but we try each one, and the first that be okay, it's all the subtree is okay. So I will try to open the door, but this task could be failed. If this task could be failed because I need a key to open the door, so I will continue and go to another sequences that will try to unlock the door and finally open it. But could be in the task unlock the door, I will check that I have the correct key for the door. But could be I did not get the correct key, so all this stuff could be failed. So finally I could smash the door. And after all these possibility tasks, I will walk through the door. So from this diagram, I describe a complex process with a lot of steps. The three main components that I use is the task. This is a simple abstraction to say, okay, do something. This is very easy to understand in your programming language because it's just a method name, but behind this task, you will check your context with the environment of your video game, basically, to know if the task is doable or any context you want to test. After that, I have the sequence, so the arrow symbol, that it just do the next task if the previous task succeed. And the selector, this is in fact like the Boolean OR, because in fact it is do the next if the previous task fail. So in the selector, I don't do the task. I don't do all the tasks because I just do only tasks that say okay or fail, and I stop to do task if at the first succeeded task. Okay. This is I show you the representation as of a behavior tree as a diagram. Now I will explain behavior tree as a piece of code. The main part of a behavior tree, we will describe task. So I create a class task, and at each step of my process, I will call a method that's named tick. A tick is related to time in a video game, but in our application or our problem, here, tree matching, the tick will be something else. But the important thing is that this method, tick, do something and return a status. The status of the task done. But the status is not just a Boolean function, fail or success. It's a special enum with failure, success, and running. So the first part is a task could say, okay, I didn't finish, so just say running. So you need to test me again in the next tick. So after define the classical blocks, the task, I will create nodes and also the root, define the nodes and the roots of my tree. So I need to create tree, and each node and roots of tree is related to child. So when we create a tick method for a tree element or task, I will be related to my parents and to my child, because with this block I could be inside the tree, and the task block is the leaf, so I do not rely to anybody. With this, I could define my famous arrow symbol, so the sequence. So the sequence, the tick method in the sequence could take user data and return a status, but in fact is related to child. So for each child, I just call tick on the child with the context, donc user data, and get his status. And I will handle this status as a task. So if my status is running, I'm also running. So recursively, from the leaf that say running, all my behavior tree could say, okay, I didn't decide what I've done. If I fail, I stop and all the sequences fail. And if I could check all my child, the sequence is a success. So I return success. After the sequence, we have selectors. So the selector is like OR. So in fact, we tried all childs. We check the status. Like sequence, if the subtask is running, I'm also say running. But if subtask success, I stop. I say success. And if all my child fail, I'm fail too. Okay. With all that, we have just 3 basic blocks, but we could imagine another blocks. So if I understand the concept of any part of my behavior tree could say fail, success, or running, I could create, for example, a concurrent block that will propose to test each child concurrently. So I could, in the position of selector just run a test and call tick on each child in order. But here, I will call tick in any child. So I will enumerate my child, store in a status list all status of all my child. Of my child, child 1. And if all my child 1 has finished, I did not. didn't have a task still running. All my child could be fail or failure, but never running. I could check. I need only one success to say I'm successful. If I didn't have only one success, I fail. My concurrent test, my concurrent block say fail. And if I still a running task inside my child, I'm still running. So with this kind of abstraction, I could, in a synchronous way, manage asynchronous processes, notably with the concurrent abstraction. So this is the presentation for the concept of behavior trees. And now, how to use it in a precise use case, that is tree matching. Tree matching, in fact, it comes at any moment where you need to do some data validation. You have a complex data representation inside your application, and you need to identify inside this big data tree some form and validate that is correct or incorrect. You could use tree matching when you want to do some data transformation because you want to match some form and rewrite inside your tree only this kind of data. And more generally, you always need tree matching when you want to do some data generation because you have a first data tree that you will traverse, identify some things, and call some other method that create another type of data. So you could have a first data tree that generates a second data tree. And in fact, all these use cases are in fact inside the compiler. When you want to identify some pattern in your big data tree, this is a semantic check because the semantic, the meaning of what you write in your language represent into an IST, in fact, is a good construction, good tree construction. All IST transformation could be done with tree matching, and at the end, code generation is basically tree matching. All this stuff, in fact, are already done with functional language like Haskell or another language that support pattern matching. Pattern matching is a statement, a powerful statement in this kind of language because you could easily match partially a subtree, a tree and partially a subtree. To basically do a tree handling, you begin to write a recursive function that traverses all your tree in a top-down way, and use a pattern matching to identify node, deconstruct it, and do something with it, and call some piece of code. This could be useful for a major part of your stuff, but when you want to do some tree reconstruction, to identify some part of code, some part of the data and rewrite it, you are not in the good way. You can't match in a top-down way because you begin to match roots before leaf, so you can't rewrite leaf. This is finished. So if you want to do some tree reconstruction, you need to match it and identify your tree in a bottom-up way. And if you have more complex pattern matching that are deepest from only one level, because you want to match an ancestor and a child deep at a 2 or 3 level, because you want to check a special construction inside a statement for language and other stuff like that. Basically, pattern matching is not enough. So for all this kind of stuff, I think about behavioral trees, and I have an intuition to test. That is, okay, behavioral tree is a certain way to do a finite state machine, but in academic definition, a behavioral tree is called it's like a hierarchical state machine. This is a kind of automata more adaptable and more versatile than the basic finite state machine. You don't have explosion of states. You have a lot of good properties. So I try to use this kind of new way to describe automata, behavioral trees, to identify and to do tree matching. The main idea is to have a walk method that allows us to traverse our data tree in the correct order, so bottom up, and to notify our behavioral tree. And the other good part, it is that a behavioral tree, it's a good representation and mimic a pattern. For example, I will describe for my tree matching module, I will describe a pattern of a tree, and this pattern is easily transformed into a behavioral tree using the concurrent abstraction. So, for example, here, this is like a generic representation of pattern matching with a data structure in Python. I begin to match a value. If this value is of the correct types, if this value types, it's inside the attribute name. If this sequence is okay, concurrently, I could match other parts, other things that could exist inside the Python data tree. And with all this, I could quite easily translate my pattern into a behavior tree. And it's also versatile because my need is to do traversal in bottom up to allow reconstruction, but in fact, if you change some inverse some line of code, you have again a top-down pattern matcher. So it's completely versatile. You could use it in both ways. So let's create a generic Python tree. I create a class. I just do a mapping of keywords, parameters inside my attributes. So with my class, I could simulate any class with attributes. I create also something related to a dictionary. To simulate the things that you could also match a dictionary to match a key or the value part of a dictionary. It's the same thing for a list. And this could be a data tree, a small part of a data tree that represents our challenge. So I could have an attribute, and a list. Inside the list, I could have a dictionary and things like that. And to handle this kind of data tree, I need to rely to the basic reflection mechanism of Python with vars and get.attr to iterate through attributes, and some types of collections module like mapping and iterable to know if my object is like a dictionary or is like a list, and use yield and yield from because my traversal function will be used as a generator, and my traversal function is also recursive. So I will send notification through a yield statement but my function is recursive, so my recursion must be yield from. If you understand the previous presentation, you understand why use yield from here. Okay, this is a generic pattern of a universal working function that iterates for any tree in Python. I'll hide some data here. The big step is to identify what kind of tree I traverse. So my tree is it related to a mapping or an iterable, and at the end I directly iterate through common attributes. At each part I yield from recursively my work function into the child. So this piece of code iterates any data tree. And at each hidden port, in fact, I do notification. I do notification to yield, okay, now I have matching a value. This is the value of the data. I have match, oh, je suis parti loin. I have matching a type, this is the type. This is the name of the attribute, this is the name of the key, this is the index of the list. With all this information, I could send it to a behavior tree that compose and do pattern matching. And with this, I could identify a value or any value, type, a component attribute, a list or dictionary, list, attributes, etc. So with all this stuff, I have one pattern, one subtree identified, but I need to do some more smart stuff, because you could have a tree inside trees, things like that. So I need just to identify a single tree, but a forest. So to identify forest, in fact, one pattern is correctly one behavior tree, but in fact, I do n concurrent pattern n behavior trees with the concurrent abstraction. When I walk and traverse my tree, I must be aware of the storing of status and positioning inside my tree. So I can't store it inside the behavior tree, because the behavior tree represents the pattern, not the actually partially identified sequence. So I need to create another store to store this sub-element. So my self.status, my previously self.status that allow me to store the current status of a behavior tree are now stored in the user data. User data, it's another parameter provided to the behavior tree. So you have the behavior tree that that represents the structure of a pattern, and all the data and the current element are defined by another structure. And you need also to clean, because you begin to identify with your behavior trees, and sometimes behavior trees fails. So you need to clean up during the traversal of trees to be aware when a correct sequence are reached. Okay, I took all this and I put in on a module called tree matching on my GitHub. Soon I will distribute it in PIP. Basically, you could use a bunch of class that allow you to describe pattern. In fact, it was an embedded DSL through Python classes. So you could have, for example, match any type with the class any type, a list with at any index I want a type str with this value, etc., etc. I could just describe attribute and precisely this attribute. I want a foo of type int for any value. I don't care. I put it. I describe my pattern as as encapsulation of data of class instantiation. I send it to my matching battery, and after that I use a match method on my data tree, and the stuff are done. You could manage all these things. You could capture nodes and callback function. After some cleaning and bug hunting, I need to write some documentation. After all that, I could send the module on pipe. Okay. I don't think we have a question. See? No? One question? One question? Any question? No? Okay, thank you.